This tutorial will be discussing writing and balancing chemical equations. Chemical reactions are a process in which one or more substances are converted into one or more different substances. Notice that the substances are still there. The actual atoms themselves are there at the beginning and at the end. They didn't actually change form. They just changed what they're bonded to. And this follows the conservation of mass, which states that the mass at the beginning will be in the mass at the end. We've talked about this previously. So even though the atoms are rearranging, they're bonded to different things, they're still there, so the actual amount, the actual weight of it's not going to change. For example, a combustion reaction is a type of chemical reaction in which a substance combines with oxygen to form one or more oxygen-containing compounds, and in the process it emits heat. So in this tutorial, we're going to be discussing how we're going to represent this, and that's through chemical equations. Chemical equations are a shorthand way of describing a reaction. They balance both the mass and the charge of each particle. They provide information about the reactions. They provide information about the reactions formulas of reactants and the products, the states of the reactants and products, and the relative number of reactants and product molecules that are required. They can be used to determine the weights of reactants used and products that can be made. In chemical equations, the same atoms are present in the reaction at the beginning as in the end, so the amount of the matter in the system doesn't change. And this is called the conservation of matter. Because the principle of the conservation of matter, the equation must always be balanced. It must have the same number of atoms of the same kind on both sides, meaning there's an arrow that's dividing the reactants and the products from one another. And the amount of atoms on the left side have to be the same as the amount of atoms on the right. And this is all based on and this is what stoichiometry is based on. Stoichiometry relates the compounds to one another and identifies the relationship they have to one another. They're the coefficients that you multiply the entire compound from to make sure that things are balanced out, and we're going to be discussing that this tutorial. These are the stoichiometric coefficients. So when we're reading this chemical equation, the left-hand side are the reactants. Those are our starting materials. Our right-hand side are the products. That's what we're going to end up with. So you can read this in a couple different ways. We can say 4 iron atoms are reacting with 3 oxygen molecules to form 2 molecules, or 2 formula units, of Fe2O3. Or we could also say 4 moles of iron and 3 moles of oxygen yield 2 moles of iron 3 oxide. Remember, we can relate these two terms by Avogadro's number. Which is 6.022 times 10 to the 23rd. So what we're saying here is, instead of saying atoms, we can say we have this many atoms, 4 times this many atoms, plus 3 times this many molecules, to give us 2 times this many molecules. And that's why we can replace that with moles. So the chemical equation depicts the kind of reactants and products and how they relate to one another. The numbers in front, once again, are called the stoichiometric coefficients. You'll notice the letters here in parentheses. They're stating the physical state: solid, gas, liquid. This is aqueous, meaning it's dissolved in water. Sometimes you'll see a double arrow in the reaction. That means that the reaction can go forwards and it can go backwards. And it means that it is at equilibrium. So let's get some practice in balancing these chemical equations. The first thing you need to do is make sure that you have the same elements on the left hand as you do on the right. The ultimate goal is to get the same quantity of elements, quantity of atoms on each side. So let's figure out what elements we have first. We have carbon, hydrogen, and oxygen. On the left hand side, we have 3 carbon, 8 hydrogen, and 2 oxygen. On the right hand side, we only have 1 carbon, we only have 2 hydrogen, but we have 2 oxygens here and 1 invisible number here. Notice the plus sign here, we have to add that together to get us 3. Now we need to make sure that the left side equals the right side, and we do that by multiplying by the stoichiometric coefficient. So to get the right hand side here to make 3, I can multiply this by 3. So I'm multiplying the entire compound by 3. So I have 3 carbons. This now changes our oxygens. So instead of having 3 oxygens, I now have 3 times 2, which is 6, plus another one from over here, is equal to 7. Notice I put the number in the front. Think of it as algebra, as if we're saying 3 times x plus 2, and we distribute it. This is being distributed to both elements. Alright, so let's look at hydrogen. We have 8 hydrogen on the left. We only have 2 on the right. We can multiply this by 4 to make this into an 8, because 4 times 2 is 8, but that messed up our oxygens again. So we no longer have 7. We still have 3 times 2. We still have 6. Here now we have 4 times 1, which is equal to 4. So we have 6 plus 4. We have 10 oxygens. So in order to get 10 here, we can multiply that by 5. And because there's no other elements there, it doesn't actually mess up anything else that we've already done. Let's try this again. First thing you want to do, write down all your elements. B, H, O. We have 4 boron, 10 hydrogen, and 2 oxygen on the right. On the left, we have 2 boron, 2 hydrogen, and 3 plus 1 oxygens. Alright, so we have borons, we have 4 and 2. Let's multiply that by 2, and that changes our boron to 4 now. That also changed our oxygen. We now have 2 times 3 to make 6, plus 1 is 7. Let's look at our hydrogens. We have 10 on the left, we have 2 on the right. If we multiply this by 5, we can change that to a 10. That also changed our oxygen, so let's cross this out again. We still have 6, now we have 5, which gives us 11. Now, when we look at the left-hand side over here, because no matter what, we have to multiply by 2 to whatever coefficient we put here. So there's no way I could possibly get 11, because 11 is an odd number, and no matter what I put here, it's going to come out to be even. So the easy way to do this, the shorthand, is to do 11 over 2. But the problem with this is we can't have a fraction there. We want whole numbers. So we multiply the entire equation by 2. So there's invisible ones here. So 1 times 2 is 2. 11 halves times 2 is 11. 2 times 2 is 4. 5 times 2 is 10. So the final answer is then 2B4H10 plus 11O2 yields 4B2O3 and 10H2O. Notice that the physical states didn't really matter when we're balancing. It'll matter in other instances, but not with balancing. We're going to do one more final example. Once again, figure out your elements N and Cl. We have 1 nitrogen and 3 chlorine, 2 nitrogens on the right and 2 chlorines on the right. So to make this come out, multiply NCl3 by 2, and that changes the nitrogen to 2 and the chlorine to 6. Then on the right hand side, if we multiply this by 3, that changes it to 6, and everything gets balanced out. This is a little bit easier. Notice I didn't put any number here. There's an invisible 1. You don't actually have to write the 1, but know that there's a 1 there, saying that there's 2 nitrogen trichlorides to form, or breaking down to form 1 nitrogen gas and 3 chlorine molecule gas molecules. Alright, in this tutorial we discussed how to balance chemical equations, and I hope it was helpful.